Hello everyone, I'm Aria Rezaei and this is my presentation on application-driven privacy-preserving data publishing with correlated attributes. The motivation of our work is that usually data is collected for a specific target application, and then there are some concerns by the users about specific sensitive attributes. We propose a framework called PRGAN, which allows us to publish a dataset that guarantees high performance on target application while hiding the sensitive attributes. Our work is inspired by recent advances in adversarial samples, where the goal is to fool a classifier into misclassification by adding some noise to it, usually unnoticeable by human eyes. One of the most commonly used tools in the literature is generative adversarial networks, in which two classifiers play in an adversarial game. There is a generator, which tries to generate fake samples, while a discriminator tries to detect whether a given sample is fake or not. These two are trained alternatively until they converge. And the final result is that the generator will be able to create fake samples that look just like the real ones, as you can see in the picture. Suppose that the dataset includes entries of n individuals, each having a feature vector along with a target label yi and a sensitive label zi. Suppose also that there is a partial conditional distribution of z with regards to y that is known to the public and the adversary. For each particular value of y, we know the probability of z given y for a subset of z. This subset could be empty when there is no prior knowledge in this regard. An example of that would be the case where the dataset includes pictures of people's faces. Target label is gender and the sensitive label is identity. Assume that there are 10 male subjects and 5 female subjects. Of course, the adversary knows about the target label since we intend to publish it. And now, given that a specific image has gender equal to female, of course it couldn't be one of the 10 male subjects, and vice versa. The goal here is to generate a perturbed dataset X prime such that a predictor for the target labels Y still performs well on X prime, while a predictor for the sensitive labels Z fails to perform well on X prime. In our paper, we proved that an adversary's predicted probability of Z given Y for an optimal answer X star should follow the maximum entropy distribution MED of Z with respect to the prior knowledge. So what MED does is that it basically assigns the same probability as the prior knowledge wherever it exists and distribute the rest of the probability uniformly across all the other possible cases. In other words, for each target label Y and sensitive label Z, if the probability of Z given Y is known, then MED is just equal to that. Then the remaining probability is distributed evenly among unknown instances. And below you can find an example of MED for 6 subjects when 2 of them are male and 4 of them are female. With that said, we're going to move on to the architecture of our model. As I mentioned earlier, there's going to be a generator G, which is in charge of creating perturbed data, and there's also going to be a discriminator D. On top of those two models that are present in the original GAN architecture, there are going to be 2 other models. One of them predicts the target labels here called dy, and the other tries to predict sensitive labels here called dz. The loss function is comprised of 3 parts. So the first part and the most important part is where we ensure that the target labels y are predicted as accurately as possible while there is maximum confusion about z, the sensitive label. We do this by keeping the prediction loss for y as low as possible while minimizing the difference between the predicted probabilities of z and MED, maximum entry distribution that we discussed earlier. The next part is the original adversarial loss between G and D in the original GAN paper, where the discriminator tries to distinguish between real and fake data points, while the generator G tries to fool the discriminator D. And finally, we use regularization in the form of a hinge loss to limit the amount of noise that is added to the data. This is known to stabilize the training process and speed up the training of the GAN. We can now move on to the experiments and results. First, we take a look at the datasets that we have used. Here we use 4 datasets in total. The first one, which is kind of a toy example, uses the MNIST digit dataset. This dataset is comprised of about 60,000 handwritten digits between 0 and 9. Here we define the sensitive labels to be whether or not a digit is bigger or equal to 5, and the target label is that whether a digit is odd or even. The partial knowledge then comes by definition. So for instance, given that a digit is odd, the probability of it being bigger or equal to 5 is 60%. It's 3 out of 5. Next, we use the public celebrity faces, and after filtering out subjects with too few images, there would be 15 subjects remaining, 10 of them male, 5 of them female. We define the sensitive label here as identity and the target label as gender. And the partial knowledge, of course, comes by definition. If a candidate or a picture is for a female candidate, it couldn't be one of the male subjects. The third dataset that we use is the UJI indoor localization dataset, from here on called the Wi-Fi dataset. This dataset includes the Wi-Fi signal strength of about 21,000 locations across 3 buildings and 13 floors in total, and there are 520 Wi-Fi access points in total. The target label here is which floor a person is on, and the sensitive label is which one of the 8 sections on each floor a person is in at any moment. The partial knowledge that we have is basically that given that a person is on a specific floor, it obviously is in one of the 8 sections on that floor. It couldn't be on a section that is on a different floor. The fourth dataset that we use is the Occutherm occupancy dataset. So Xbox Connect devices are mounted on top of a door, and people that are moving in and out of a room have their depth black and white images taken. There are more than 15 subjects in total, and the top 20 subjects with most images are used in our experiments. Each of them has about 2,000 images in total. The target label is whether a person is moving in or out of the room, and the sensitive label is identity. In this case, there is no partial information between Y and Z. There are 2 major groups of prior work that we compare our method to. The first one is when the generator simply tries to fulfill the demands of the target classifier dy while beating the sensitive classifier dz. So it's basically our own architecture, except that there is no discriminator of the GAN d. The second one is where the generator simply tries to fool sensitive classifier dz with the help of a GAN discriminator d. So it is our own architecture, except that there is no target classifier dy guiding the generation of the noise. And the third group, we also compare our method to differential privacy mechanisms such as the Laplacian mechanism and randomized response. You can see the result of our experiments across the 4 datasets here. For each of the datasets, we have set a minimum threshold of performance for dy, which is 95% across the 3 image datasets and 75% for the Wi-Fi dataset. And then we've tried to minimize the prediction accuracy for DZ using the 4 methods, PR again, and the 3 baselines. And at the bottom row, you can see what a random classifier could do given the prior knowledge that we had. First, look at the vast difference between the performance of the first 2 methods, PRGAN and NGP, and the other 2 methods, adversarial privacy and differential privacy. In the latter 2, there is no target classifier dy to guide the generation of the noise. And as you can see, with dy in place to guide that noise generation, we can achieve a lot better results here. Also note that across the 4 datasets, our method PRGAN is outperforming naive generative privacy by a couple of percentage points. And this difference gets more pronounced in the 2 more complex datasets of PubFake and Occutherm, which includes complicated images. This means that the GAN's discriminator D helps the perturbation go the extra mile. As expected, differential privacy produces the worst results. This was expected because DP is oblivious to both of our objectives, and any method that is ignorant of the two objectives, cannot find the right trade-off between privacy and utility in our scenarios. Now the question is, how do the four methods fare with different utility budgets? Utility budget here is defined as the maximum allowed drop in the accuracy of prediction on Y. And the goal is to have the highest decrease in the accuracy of prediction of Z. And as you can see, PRGAN is outperforming all the other baselines in this experiment with different utility budgets. This experiment was done on the Wi-Fi dataset. A major advantage of our framework is that once trained, the noise generator G can operate without any further data. This allows it to be trained at a facility with as much computational resources as it requires, and then to be shipped to other users' devices for user-side noise generation. For that to happen, we need to have generator models that are simple enough to run efficiently on mobile devices. Two metrics that are commonly used to measure the complexity of a model are the number of floating point operations and the number of trainable parameters. In the table below, at the top 4 rows are state-of-the-art mobile networks designed specifically to run on mobile devices. At the bottom 4 rows are the models that we have used to generate perturbed data. And as you can see, all of them are less complex than the state-of-the-art mobile networks, which means that it is possible to run them on mobile devices efficiently. Previously, the model was trained on clean data and inference was done on perturbed data. This corresponds to the case when users send their data to a cloud for inference and they need to perturb it before sending it out. Now the question is, can we train the model on perturbed data and then do inference on clean data? This corresponds to the case when model is trained on public data and then it is used on users' devices to do inference on device. In the table below, we have the target classifier accuracy for the two cases. And as you can see, in the case when training is done on perturbed data, the performance is very similar. This means that the perturbed data could be used for training purposes as well. Finally, there is a question of transferability of our results. Can a noise generator learn to hide identifying features when it's trained on the group A and then it is used on a separate group B? To test this, we designed an experiment using the Ocutherm dataset, where individuals were moving in and out of a room. Previously, we trained a noise generator G on the top 20 individuals with the highest number of images. Here, we also trained a target and sensitive classifier on the other 30 individuals. We used the generator G to create perturbed samples for these 30 individuals, and then we test the classification accuracy for the perturbed data on the sensitive and target classifier that we just trained. And the results are in the table below. As you can see, with a slight drop from 95% to about 87%, we get almost perfect hiding of Z. A random classifier can perform at 3.3%, while here we have achieved 3.7%. This concludes my presentation. If you have any questions, I'd be more than happy to answer them.